When light enters glass, the direction that light travels changes or bends in a process called refraction. If the surface of glass is curved appropriately, we produce a lens, which can magnify, diffuse, or distort the light rays from objects in the background. Since gravity causes light to travel in curved spacetime, any object with a gravitational field appears to bend light as a gravitational lens. The examples that we looked at earlier, like this image of the Cheshire Cat Galaxy group, were cases where the light was emitted far from the closer lensing mass. In this image, the arcs making the smile and outline of the face are images of galaxies lying far behind the eyes and nose galaxies, whose mass is warping spacetime. However, if we consider ultra-dense stars with gargantuan gravitational fields, the light they emit will also travel on curved paths. Neutron stars are examples of stars with strong enough gravity that they exhibit gravitational lensing. Their emitted light travels part of the way around the star before it can escape to be observed by telescopes. By observing how light is bent around neutron stars, we can understand the properties of these stars better, which will help us keep from confusing neutron stars with black holes in the future. If you look at my head, you can only see the front of my head, and you have no way to know what the back of my head looks like, unless I turn around. This is because in situations with weak gravity, like here on Earth, light travels on straight paths from my head to the camera. But if my head was really heavy, so that my head had a gravitational field as strong as a neutron star, then light originating from the back of my head will travel on a curved path around my head and be captured by the camera. This would give you a distorted image of my face, surrounded by all of my hair, and as a result, my head would look larger than it really is. This animation shows the effect of a neutron star's gravity on the light that it emits. In these cartoon animations, we show a dim star with one bright spot on it. The left animation shows an image of the star as though its gravity has no effect on the light that it emits. In this case, we see the hot spot for only half of the rotation period, and it is eclipsed when it is on the backside of the star. Since the hot spot appears brighter than the surrounding star, a plot of the overall brightness would increase as the hot spot rotates into view and decreases as it becomes hidden again. The right animation shows the same star, but now it includes the gravitational effects. The star's strong gravity causes the light emitted by the star to travel on curved paths, so that parts of the star that would normally be hidden are distorted into view. The strong gravity allows us to see the bright spot all of the time, even when it is on the backside of the star. The star's gravitational field distorts the circular spot's image so that it looks like a thin curve, and it allows us to see around the spin poles. Since the hot spot is now visible throughout the rotation of the star, there is much less variation in the overall brightness with time, as shown on the graph below the animation. The star is rotating so fast that the equator is moving at 30% of the speed of light. When the spot is moving towards us, the light it emits is blue shifted, and when the spot is moving away from us, it is red shifted by the Doppler effect. When light is Doppler shifted, there is another relativistic effect called Doppler boosting, which makes the blue shifted light appear brighter and the red shifted light appear dimmer. If you pay attention to the brightness scale on the right, you'll notice that the spot is brightest when it is moving towards us, and it is dimmest when it is moving away from us. NASA's NICER X-ray telescope is measuring the gravitationally lensed and Doppler-boosted light from hot spots on neutron stars. NICER is attached to the International Space Station and observes X-rays emitted by neutron stars with spots, as well as black holes. Black holes do not have a surface, so we can't observe hot spots on rotating black holes in the same way that we observe them on neutron stars. But we do know that there are light-emitting structures like accretion disks that orbit black holes. Images like this one, drawn by artists, represent accretion disks around black holes. In most pictures, the artist has drawn the accretion disk as though the black hole's gravity does not warp space-time or the paths that light rays follow. So we see the accretion disk as flat. But if a neutron star's gravity can distort the paths of light, then a black hole's can too. This vinyl record represents a crude model of an accretion disk, and the hole at the center represents a black hole. If we ignore the black hole's strong gravity, then when you look at this disk, the light rays travel from the disk to the camera on straight lines, and the disk looks flat. A black hole with an event horizon with the same size as this hole has a Schwarzschild radius of 3.6 millimeters. This corresponds to a mass that is about half of the planet Venus squished into this hole. The strong gravity of the black hole will distort your image of the back of the disk. You will still see the front of the disk since the light rays don't have to pass by the black hole in order to get to the camera. Light emitted by the back of the disk has to travel close to the black hole in order to get to the camera. Light from the back is bent by gravity to travel up and over the black hole to the camera. As a result, this back curve will appear to look like an arch over the black hole. But the disk also has a bottom that emits light. Light emitted by the bottom can travel down and below the black hole to get to the camera. The bottom of the disk will look like a second arch below the black hole. A more accurate drawing of an accretion disk around a black hole will show the disk arching over and below the black hole. The movie Interstellar features a view of a supermassive black hole with an accretion disk. The director, Christopher Nolan, wanted to have a fairly realistic view of the disk that includes gravitational lensing. So he consulted physicist Kip Thorne, who recently shared the 2017 Nobel Prize in Physics. The resulting image produced for the movie is shown here. In this image, we can see the front of the disk, the top of the back of the disk, and the bottom of the back of the disk. However, the black hole created for the movie required some simplifications. First, they wanted a black hole that would be safe for the astronauts to visit, so they did not include a jet. This suggests that Gargantua is not accreting enormous amounts of matter. They also chose a colder than usual accretion disk, which is only a few thousand degrees Kelvin, so that it emits ultraviolet, visible, and infrared light, but practically no harmful X-rays. When we looked at the light from a rotating neutron star, we saw the Doppler boosting effect makes the blue shifted side of the star appear brighter than the red shifted side. The accretion disk orbits the black hole at high speeds. The side coming towards you is blue shifted and should appear brighter than the side moving away from you. The director was worried that people watching the movie might get confused if the Doppler boosting effect were included, so they left it out from the rendering. This computer animation shows the results of a magnetohydrodynamic computer simulation of an accretion disk around a black hole. The researchers are simulating realistic patterns in the disk, which makes it easier to see the motion of the gas. At the start of the animation, we are looking down on the disk, and then we move downwards so that we are viewing the disk from just above the plane of the disk. The warping effect of gravitational lensing becomes more apparent as we look into the equatorial plane. When we are viewing the disk from the side, we can see that the side that is spinning towards us is brighter than the side spinning away from us. Light near a rotating black hole can travel on curves that maintain constant distance from the black hole, but trace out a spherical shell, like the photon in this animation. These paths are unstable, so a photon traveling on this path can easily be pushed outwards or inwards. If they are pushed inwards, the photons can cross the event horizon and become lost inside the black hole. If the photons are pushed outwards, they can escape to be seen by a telescope. Recall the black hole's innermost circular orbit for photons, or photon sphere. Photons within the photon sphere travel in spherical orbits, sometimes called the ring of fire. Within the ring of fire, there is a black region called the black hole shadow, a region where light can no longer escape to outside observers. The Event Horizon Telescope is a collection of radio telescopes scattered across many locations over the Earth. The Event Horizon Telescope is observing Sagittarius A star, the black hole at the center of our galaxy, and eventually it will become sensitive enough to detect the black hole shadow. Computer simulations suggest that Sagittarius A star should look something like this video. This computer simulation shows an accretion disk orbiting around a black hole and shows a ring of fire around a central dark feature. However, the image that the Event Horizon Telescope is creating will not look as sharp, since the picture will be averaged over time and there will be blurring due to light scattering off of interstellar gas and dust. This observation will be the most detailed image of the region directly outside of a black hole's event horizon.